Okay, here is part number 2. What I'm going to show you here is that how we can reduce the number of tests even more. And the idea is very simple. So in single pooling, we said, well, we take all these people and we put them in random order. So in what I will call multiple pooling, we're just going to do this several times. So why use only one random order? Why not use several? Okay, so the multiple pooling, it takes as input N, and C, and an S. N is again the number of people who go for the COVID test. The number of infected people is still denoted by K, but the algorithm doesn't have to know K. There is this parameter S, which is exactly the same as what we had earlier on. So S will be the block size. And additionally, there will be an input parameter C. And C will denote the number of random permutations that we are going to use. So multiple pooling does the following. We repeat these two lines here, C many times. Okay, so we say take the n people, put them in a uniformly random order. So the first time we do this, we get this random order. We divide the people into blocks where each block has size S. And then we say, well, for this particular order, we go through all the blocks one by one, and then we do the test on the people who are in block J. Okay, and we repeat this C times. So this is the first time, and the last time again, we put these people in random order. This defines blocks. Every block has size S. We go through these blocks one by one, and then for every block, we run the procedure test. Okay, so in the previous algorithm, this C was equal to 1. Yeah? Previously, we used only one permutation. Now we just say, let's do this C many times. Okay, after we have done this, what do we know now? So now go through all the people, I from 1 to n. So what can happen with person P sub I? Okay, now imagine that in one of these iterations, the test of Pi's block was negative. Yeah, so let's say the iteration where this happened was the last one. Okay, so we said we put the people in random order. Person Pi is in one of these blocks. Let's say person I is there, and the test for this block was negative. If this happens, then we know that person number I is not infected. Yeah, so person I is healthy. Yeah, so if in at least one of these iterations we look at the block where person I is, if the test returned negative, then we are sure that person number I is not infected. Otherwise, that means in every iteration, so in iteration 1, and maybe person number I is in this block, the test for this block returns positive. And for the last iteration, for the last permutation, maybe person number I is there. We run the test on this block here, and again, the result of the test is positive. Yeah, so if every time we do the C times, and every time for the block where person number I is, the test is positive, then maybe Pi has been infected, maybe not, we don't know. So then we just do the naive thing. We test person I individually. Okay, so this is called multiple pooling. By the way, this whole idea of group testing, I learned about this end of March or early April, just when the pandemic started. And before that, I didn't know about this. So I read about this Dorfman, who did this in 1943, and I read that this is actually used in practice. And then in end of March or April, some people suggested this here. As far as I know, this is not being used in the real world. Yeah, but it is still an interesting approach. Okay, so previously the C was equal to 1. The new idea is, well, why use only one uniformly random permutation? Why not use several of them? Yeah, and keep in mind, if we are person PI, yeah, if PI is lucky, then in one of these C permutations, the block where PI is returns a negative. Then we know person I has not been infected. PI is healthy. Otherwise, that means every time we do this, for this is the first permutation, the second, the last one, every time the test on the block where PI is returns positive. Yeah, in that case, we are not sure yet. Maybe PI has been infected, maybe not. So then we do the naive thing. We just test person I individually. Okay, and as earlier on, we look at the random variable x, which is the total number of times we call this procedure test when running this. And we would like to know the expected value of x. Okay, and as before, it makes sense to introduce indicator random variables. So for every person PI, there is one indicator xi. Xi is 1 if person I is tested individually, and this only happens here, and it is 0 otherwise. Okay, so what is the value of x now? It is the total number of times we do a test. Well, for one particular permutation, we call this test function n over s many times. So we get an n over s. This is for one permutation. But we repeat this c many times. So we get a c there. Okay, so this is the total number of calls to the procedure test just in this loop here. Yeah, we do c times, the c is there, and then we go through n over s many blocks, and we call it this function test. And then we have to add the sum of the xi's, because in this for loop it still may happen that we call the function test, but if we do that, we call it on just on an input consisting of one person. So we get the sum of the xi's here. Okay, so x is equal to this here. And if c is equal to 1, then we get exactly single pooling, which we saw in part 1, and then we get exactly the same expression. Okay, so now expected value of x is expected value of the sum, which is sum of the expected values. So again, we have to determine the expected value of this random variable x sub I. Okay, now as before, if person I has been infected, so this person does have COVID, then xi is always equal to 1. And why is this? Well, so take a person who has been infected. We repeat this c times. So the first time person I is in one of these blocks, maybe person I is there. If we run test on this block, the result will be positive. And this is also true for the second permutation we use, and it is also true for the last one. So if pi is infected, then xi is always equal to 1, because in that case we are always in the else case. And that doesn't matter which permutations we choose here. Okay, so this is as earlier on, so expected value xi is 1. So the question is now, what happens if pi has not been infected? What is the expected value of this random variable xi? Okay, so if xi is not infected, then it may still happen that the algorithm goes to the else case here for person I. It is still possible that we test person I individually. Now, when does this happen? This happens for this particular person pi who has not been infected. We reach this line here. This is the else case. So that means we need to negate this here. That means in every step here, the result of the function test on pi's block is positive. Yeah, so we have to determine the probability of that. So if I'm going to introduce the following events, for L from 1 to C, A sub L is the event in iteration L. Nobody else. In pi's block is infected. This is very similar to the event that we looked in the previous case. Yeah, there was no index L there. There we said, well, let's look at the event. We have this random order. pi is in one of the blocks, and we look at the event that nobody else has been infected. And remember, pi has not been infected. So then xi equals 1. So when is xi equals 1? Xi is 1, that means we test person I individually. That means we are in the else case here, which means this is not true, and the negation of this is for every iteration, the result of the test on pi's block is positive. That means for every iteration, you ask what is the block where person number I is, and then at least one of the people in that block has been infected. But that is exactly the negation of this here, of this event AL. So xi is 1 is equivalent to saying that A1 is not true and A2 is not true up to AL is not true. Yeah, so as usual, the bars here indicate complement. Yeah. Xi equals 1 means pi is tested individually. When is pi tested individually? When we are in the else case. And why are we in the else case? Because this here is not true. And if you negate this, that means for every iteration, this function test on pi's block returns positive, which means if you look at pi's block, there is at least one infected person. And that again is the negation of this here. Okay, so xi is 1. This happens exactly when A1 is not true. That means A1 bar is true, A2 bar is true, AL bar is true. And that means that the expected value of xi, as always, this is the probability that xi equals 1. And this is the probability, well, xi is 1 is equivalent to what you see on the right hand side. So I just copy this here. Okay, so now we see events that are connected by logical ends, which corresponds to intersections. Okay, now I didn't write this down here, but when I say repeat the following C times, we take a uniformly random permutation. That means if we do this a second time, the random permutation does not depend on the previous permutation. And this is true for each of these C times that we go through this here. So that means that all these C many permutations, they are chosen independently of the others. So here we have events which are really mutually independent. Because if the event A1 holds, that means in iteration 1, you ask where is person PI, maybe PI is there. A1 says nobody else has been infected. And if we look at event A sub C, we look at the final permutation, we ask where is person I, maybe person I is there. Event A sub C says nobody else in this block has been infected. And since this permutation does not depend on this one, that means the event A1 does not have any effect on the event AC. Yeah, so in general, these events here are pairwise independent. No, sorry, they are mutually independent. So the probability of this is just the product of the individual probabilities. So this is probability A1 bar times probability A2 bar up to the probability of, there shouldn't be an L here, this should be a C. And this is a C bar. Okay, so we want the expected value of xi, and now we know it is equal to this here. Now in the first part of this video, we determined the probability of this event A sub L. Yeah, because there we said we put the people in random order and we determined the probability that nobody else in PI's block has been infected. So we know the probabilities of the ALs. And we want the probabilities of the complements, but of course this is just probability of A1 complement is 1 minus probability of A1. Probability of A2 complement is 1 minus probability of A2. And the last one is the probability of AC bar is 1 minus the probability of AC. And in the first part, I denoted, so all these terms here, probability of A1, probability of A2, probability of AC, they are all equal. And in the first part, I used this parameter P. So this is just 1 minus P to the power C, where P is the same number as you saw in part 1 of the video. Okay, so now we have determined the expected value of xi, so let me write that here. If PI not infected, is 1 minus p to the power c. Okay, so now we know this here. So that means now we can determine the expected value of x. This is what we wanted. X is equal to this term plus this sum. So the expected value of x is the expected value of the whole thing. This just gives us Cn over S. Then we get an expected value of the sum, which is the sum of the expected values. And the expected value of xi, it is either equal to 1 or it is equal to 1 minus p to the power c. So how many terms are there where exi is 1? Well, that's equal to the number of infected people, which we denoted by k. So we get k times 1. And for every person that is not infected, and there are n minus k, many of them, we have 1 minus p to the power c. Okay, and if you work this out, so we take the same p as we had earlier on, then we get the following expression. It's not a nice function. Cn over S plus k plus n minus k times 1 minus n minus s choose k, n minus 1 choose k, and this whole thing to the power c. Okay, so here I took this value p that we had earlier on, and this here was the value of p. And I just plug it in, and then we get that the expected value of x, so this is the expected number of calls to the function test when you run this here, is equal to this ugly expression here. Okay. So now we have a function here, or an expression. It involves n, the number of people. The number k shows up here and there, and it is here and it is there. K is a number of infected people, so we don't have control over this. The S is the block size. S is here and S is there. We can choose the block size. And C is the number of permutations that we use, and the C shows up here, and the C shows up there. By the way, if C is equal to 1, then the expression we get here is exactly the same expression we had in the first part, when we used single pooling. Okay, so now, again, for particular n and k, this function is even worse than the previous one, so I don't know how to optimize these. Yeah, so n and k are fixed. We don't have control over these, but we can choose S and C. Okay, so now I'm going again to look at some particular examples. So I take the same numbers as we did earlier on. So n is 1,000. K equals 10. Okay, so there were 1,000 people who are going for the COVID test, and among the 1,000, 1% has been infected. So the first idea was do individual testing. Individual then the number of tests that we do is equal to 1,000. Because we have to do one test for every person. Then, as we saw in part 1, if C is equal to 1, that means if C is 1, we get a single pooling we saw in part 1. And there we saw if we take as block size S equal 10, then the number of tests reduces to 196. So we go up to 4. Okay, so now you should open the PDF file of the notes. And before, or in part 1, when C equals 1, I showed you this graph that I got from Wolfram Alpha. I did the same thing for C equals 2, 3, and 4. So for every particular value, I entered this formula where n is 1,000, k equals 10. So if, for example, when C equals 2, I entered this in Wolfram Alpha. Wolfram draws this function for me. You look at the function and then you find the value of S for which this expression is minimized. If C equals 2, so the number of permutations we use is 2, using a block size of 25, then the expected value of X, so the number of tests that we do, instead of 196, it becomes 137. Okay, so just a simple idea of, instead of using one random permutation, we use 2, then we go down from 196 to 137. And again, in the notes, you can see the graph. If C equals 3, then we take a block size of 38. That gives the minimum. And then the number of tests is only 120, so we save even more. And if C is equal to 4, again, so the C now becomes 4. You plug in N, the K, and the C. Wolfram draws this graph as a function of S. And you look at this graph, and then you see when S equals 50, so we have a block size of 50, then the expected number here becomes something like 150. Okay, so this here shows that by increasing the number of C, so the number of permutations, if you make it bigger, then the number of times we have to call this function test, it goes down all the way to 150. Okay, now I didn't try C equals 5, so I stopped here. But at least you can see here the naive way to do the testing. You test every person separately, then the number of tests is equal to 1,000. If you use this simple approach here, then if C equals 4, so you take 4 random permutations, you take a block size of 50, then the expected number of tests you have to do, instead of 1,000, it's only 150. Yeah? So this is about 1/10 of the naive approach. Okay, so this was how you can use indicator random variables, how we can use linearity of expectation to solve a problem that occurs in the real world. Okay, so I have shown you single pooling. Yeah, this was invented in 1943, and this is actually used. It's a very simple idea, but very powerful. And then this year, either end of March or beginning of April, people suggested instead of using one permutation, why not use more? And then the number of tests that are needed is reduced even further. Yeah, so as I said, single pooling is used in several countries in the world, and as far as I know, multiple pooling is not used yet. Maybe it will be used. Okay, so in the notes, if you go to the last page, there are 2 links to Wikipedia pages. So the first link, it gives you to the Wikipedia page on group testing. That page is pretty good, and it is quite long and detailed, so there you can read more about the history and about other fields where group testing is used. And in the second link, this is another Wikipedia page, and there you will see a list of countries where single pooling is actually used for COVID. Okay, so this is the end of part 2, and you will see me again on Friday.